pupils. Tonight we're going to Mars. And just to remind you, Mars, am I supposed to be up there, or is this the way it's supposed to be? I mean, these people don't really need to see an I guess, is that for the other people who are looking on? Whatever. Okay. Anyway, Mars is hard. So all of those little yellow stars up there are failures on the way to Mars. I actually, thinking that there might be some Chinese students in the audience, I put the little red rover there to commemorate the Chinese first rover landing on Mars. Good for them. But we have yet to send humans to Mars. And there's Mark Watney. You've all seen The Martian, I'm assuming. I hope so. I want to talk about looking ahead to when humans finally do go to Mars, what they're going to do, how we're going to take care of them. This is not the lecture that I had originally loaded. Can you hold off on just a minute and let me see if I can, what in the, I'm going to disconnect here for a moment. I apologize. I had this loaded up before. Let me, the recent, oh boy. That's embarrassing. No, it's not. Post-oxygen MOXIE talk, ISU MOXIE talk, that's what I wanted. Sorry about that. Let me get rid of this. ISU MOXIE talk, okay, can we hook up back now? Is that still going to work with everything? Sorry about that. All right. Now we'll go back to Mars, and my apologies. We still got Mark Watney. What I wanted to do, because we have a little bit more time than when I give a typical, 40-minute lecture or something, I wanted to spend a little bit of time talking about why Mars is important, why we're so interested in it, because way back when, in the early days of the solar system, when the initial stuff was coming together to form the planets, it was a pretty rough time in the solar system. We were getting bombarded by rocks. This is the early history of the Earth, okay? And there's always questions, where did the water on Earth come from? And it may have come from, we're close enough to the sun that when things first started coalescing, very likely a lot of the water evaporated. So people have been asking where all the water came from. May have been a comet bombarding the Earth. Some of it got trapped inside the Earth. We know that both carbon dioxide and water come out of volcanoes. And so, in the early Earth, it was when the Earth finally did cool down, we had oceans, we had a lot of gas, we have these, smokers in the ocean, and at some point, fairly early in the life history of Earth, almost as soon as things calmed down, we believe that that's when life actually started here on Earth. Still a lot of mysteries about it, but life started almost as soon as the conditions allowed it. And that's important when we talk about Mars, because, you know, we have these, you know, oceanic water conditions on Mars, and where those oceans once were, of course, a lot of those rocks have now been pushed up, and they find these Precambrian fossils in very specific layers of rock in Australia, in a few other places around the world. And in those are these single-cell organisms which probably represent some of the very earliest remnants of life here on Earth. This is a scale of, you know, that scale down there is about 200 microns. So, you know, we're looking at very tiny stuff here. And there are remnants in some of these stromatolites which are strewn around, where you have remnants of this very primordial single cell. Why is this bouncing around? Of this single cell life. And then fairly early on, and again, it took a while, and we don't completely know the whole story, but those single cell organisms started to form together, and you have the whole chain of life, which I'm not going into. This isn't a biology lecture, but the point that I want to make is that early conditions on Mars were probably very similar to early conditions on Earth. Remember, Mars is only about half again as far from the sun as the Earth is. Mars presumably was bombarded by the same kind of comets bearing water. Mars, we know, had active volcanoes which put carbon dioxide into the atmosphere. Mars, we believe, once had an atmosphere that was thick enough to support liquid water on the surface. The Mars orbiting observers have given these, you know, you look, if this were a picture taken on Earth, there's no question this is a drainage pattern of a river system. You always have to be a little bit careful. Just because something on Mars looks like something on Earth doesn't necessarily mean that it's exactly the same, but it sure is suggestive that there was a time early in Mars history, and this is one of the things that the Spirit and Opportunity rovers have demonstrated, that there was a lot of water. There's even speculation that there may have actually been an ocean. The northern hemisphere of Mars is at a lower elevation than the southern hemisphere, which is why we tend to land our rovers there. And there are indications of an ancient shoreline. Some of the Mars experts tell me that this may be a little bit of an exaggeration, that there was a big ocean like this, and I won't get into that. But the point is, Mars originally seems to have been very different from the Mars we know today. It had an atmosphere, it had the capability at least of liquid water on the surface. So what happened? Well, of course, you'll hear a lot about our friend the sun, which of course provides the radiation, the warmth that keeps us alive. But it's also, it's a pretty rough neighborhood when the sun decides to send eruptions our way. You're going to hear about a super eruption that Jim Green is going to talk about on Friday, the Carrington event. But this is typically what happens when you get a solar flare that hits the Earth. You get all these charged particles racing towards our atmosphere, but the Earth has a magnetic field which deflects most of those charged particles, and so they leave us relatively unscathed. Now, that magnetic field, of course, we believe is maintained by the rotating iron core inside the Earth, which is liquid because the inside of the Earth is very hot. What we think happened on Mars is Mars is much smaller than the Earth, so it cooled off faster. The liquid core of iron presumably solidified, the magnetic field collapsed, the solar wind now impinged directly on Mars' atmosphere, and because the planet had cooled off, the volcanoes were no longer active, so they weren't putting more carbon dioxide into the atmosphere. Mars lost most of its atmosphere, lost most of the greenhouse effect, it cooled off, and Mars is now the cold and dry desert planet which we have been exploring with our robots. But what might have been way back when, before all these bad things happened to Mars? If you go and drill really deep into the surface of the Earth, you can actually find these little organisms, bacteria, which have figured out how to live a kilometer or so below the surface of the Earth. They metabolize rock. There's a little bit of water down there. Now, if there ever was life on Mars, and it probably never had a chance to develop beyond single-cell organisms, but maybe it figured out a way to go underground like life did on Earth. I mean, you take a little organism like that, if we got rid of the Earth's atmosphere and the surface of the Earth, God help us, turned into what Mars is like today, those little organisms wouldn't have any idea that anything had changed. They're way below the surface. You know, they're fat, dumb, and happy. Maybe there's organisms still on Mars. Maybe there's remnants of past life on Mars. That's what we want to look for. But pretty clearly, if you're going to look for things underground, you got to drill. Now, the European Space Agency was planning to launch ExoMars, which actually was going to drill 2 meters. Granted, we don't know how deep these things might be, but it would be a start. We've never drilled that deep on Mars before. Unfortunately, I hope you know the story. The parachute for ExoMars didn't work during some of the final testing for the launch back when the Perseverance was launched. And so they had to wait. You know, Mars goes around the Earth every 2 Earth years, and we go around every 1 year, so we actually come together every 26 months. And given our current rocket technology, you can only launch to Mars during those 26-month windows. So the European Space Agency had to postpone the ExoMars launch, which was going to go on a Russian rocket this past launch window, but because of the Russian situation in Ukraine, that got canceled, and the European Space Agency is still looking for a ride and trying to put together the resources to be able to get ExoMars going. But in any case, drilling on Mars is difficult because you've got to do it robotically. Some of the students at MIT recently competed in a NASA competition where they set up a big freezer chest with ice on the bottom, and then they put all sorts of regolith, like Mars regolith, on top. And the purpose of the contest was to develop a completely hands-off robotic system that would be able, first of all, to drill down to the ice and then melt it and come up with extractable water. These are just a few pictures to give you an idea of the complexity of what we did. That's the heated core. And if you want to drill much more than a couple of meters, it's going to be almost impossible to do that robotically, which is why, you know, ultimately the search for life or ancient life on Mars, I think, is going to have to be conducted by human astronauts, you know, basically drillers, roughnecks, but people who know how to operate deep drilling equipment. And that means we're back to how are we going to get Mark Watney home from Mars, okay? Now, again, you've all seen the movie. He made it just fine in the movie, but one of the things that they never dealt with in the movie was, where did all that propellant come from? That was a pretty big rocket, probably 50 metric tons sitting on the launch pad. On the Earth, propellant fraction is typically over 90%. Mars has not quite so much gravity, so you can probably get away with maybe 80% propellant fraction, but that still means you're going to have about, in a 50-ton spacecraft, 40 tons are going to be propellant. And you probably are going to use oxygen methane. 3/4 of that propellant, or 30 metric tons, are just going to be pure oxygen. How are we going to get that oxygen into the rocket? Well, you could bring it all the way from the Earth, right? But here's the problem. Anything that you want to bring from the Earth to the surface of Mars, you've got to put a lot of stuff in Earth orbit. You've got to put, first of all, the rocket to get there, the rocket motor, and then all the propellant you need. And we talk about a 15-to-1 ratio. In other words, to get 1 ton of anything on the surface of Mars, you've got to put roughly 15 tons into Earth orbit. So 30 tons of oxygen, that's going to take about 450 tons in Earth orbit. And just to remind you, the old Saturn V rocket, that would put about 125 tons into Earth orbit. So you're talking about 3.5 or 4 Saturn V class rockets, and those were not cheap rockets. So billions of dollars potentially. Even though launch costs are coming down, it's still a lot of money. Now, a lot of stuff we've got to make on Earth. Anything we manufacture, okay, whether it's spacesuits, computers, the launch rocket itself, we got to make those on Earth and send them to Mars. There's no way around it. But dumb old oxygen, you're going to spend billions of dollars just to send a bunch of oxygen to Mars? That's the whole purpose behind MOXIE, as I'll get into later. The New York Times got it right when they published the article that a lot of people figured, oh yeah, you're going to make oxygen on Mars because people need oxygen to breathe. And absolutely, that's true. If I went to Mars, I would very much like to have some oxygen to breathe. But I only need about 800, 900 grams per day of oxygen. And I could stay on Mars a long time before I've used up 30 metric tons of oxygen, which is what I'm going to need to get home. So we're really talking about producing large quantities of oxygen. It'd be nice if you could produce methane as well, and we might talk about that later if you're interested. But the purpose of MOXIE is to demonstrate a chemical process which has been demonstrated many times here in laboratories on Earth, of how to extract oxygen from carbon dioxide. And of course, carbon dioxide, we know that Mars has an atmosphere. It's very thin, only about 1% the density of the Earth's atmosphere, but it's 95, 96% carbon dioxide. So that is the purpose of MOXIE. It's to demonstrate, because NASA has this system of what they call technology readiness levels. If you want to count on a critical process or piece of equipment, and certainly making oxygen on Mars, I would consider critical, particularly if you're going to need that oxygen to come home, you've got to demonstrate that in the actual environment. So doing it in Mars-type environments here on Earth is not enough. We want to actually demonstrate that Mars doesn't have any unexpected surprises for us, and that's why we're sending MOXIE to Mars. So this is just a mock-up, and you can see the acronym there. Whoops, Mars Oxygen ISRU Experiment. And ISR, that's a nested acronym, by the way, a second-order acronym. It's really nice. I wish we worked hard to figure out a third-order acronym, but we never quite got there. But ISRU is something you'll hear a lot about, in situ resource utilization, which means living off the land. Anything that you can use in the place that you get to. And of course, explorers have done this since time immemorial. You're going across the ocean, you get to an island. If you can find water and food on that island, you use it. They didn't need oxygen because we got plenty of oxygen in our atmosphere, but on Mars we don't, and so we're going to have to make it. So this is a model, a full size. I put it in just so you have a sense of the scale. This is the actual experiment, and I'll show you later all the different parts in it and how they work. But basically, this is the solid oxide electrolysis unit, and this is the motor and the compressor which pulls the air in from Mars. And of course, we did a tremendous amount of testing. It was actually manufactured. This is a joint project of MIT and the Jet Propulsion Laboratory. It was MOXIE was actually manufactured and went through most of its initial testing at the Jet Propulsion Lab. And then they basically, once it was launched, they turned it over to us at MIT to operate it and extract the scientific information. So I'll take you briefly now on getting to Mars. You know, first they've got to place MOXIE inside the Perseverance rover. You can see that doesn't look much like a rover now. This was in an early stage. It's actually upside down. It had no wheels on it, and so on and so forth. Eventually, the rover got put together, and it was in good shape. And then, in order to ship it to Florida for launch, they have to put covers on the wheels, and they fold things up. And then, of course, in addition to the rover, when you're landing on Mars, you need a heat shield. And I'm assuming that everybody here is somewhat familiar with how we landed. They have basically a sky crane which lowers it down. I have some pictures of that later. Anyway, you stack all those up, and let's see, up on top, this disc-shaped thing, that's called the cruise stage. So on the way to Mars, everything inside the shielding is basically inert. They turn things on 2 times just to make sure that everything survived launch and survived the transit. But basically, it was this cruise stage that does all the telemetry and the attitude control and basically gets us to Mars. And then right before we get to Mars, we dump the cruise stage, and the rest enters. Here, everything is packed up. This is packing up to ship to Florida. Of course, once they pack it up to go to Mars, they have to take those covers off the wheels and everything. But all that was done, and sure enough, at the end of July in 2020, we launched. Beautiful launch. And then we wait, and we wait. 7 months, roughly, to get to Mars. I hope all of you have seen some of the I'm not going to show the animation. There's a classic animation of the so-called 7 minutes of terror, because, of course, there's a time delay between Mars and the Earth. We have absolutely no control over the spacecraft that's entering Mars's atmosphere and has to figure out where it's going to go and land safely. All that has to be pre-programmed, and you just wait until the telemetry comes back anywhere from 5 to 20 minutes later, and you find out what happened. This is not a suspense story. You know it worked, and we were very happy. And there it is, you know, on the parachute. That parachute, in case you hadn't known, you see kind of a funny pattern on there, and this was kind of a guessing game, which I managed to decode around the outside, and it actually says, "Dare mighty things," which is the motto of the Jet Propulsion Laboratory, and then it actually gave the geographical location of JPL. So Perseverance is following in the footsteps of a whole series of Mars rovers, which began with the little Sojourner rover at the bottom left there, which was launched on the 4th of July back in 1997. And then in the early 2000s, we had the Spirit and Opportunity rovers, and what they did was to basically demonstrate that yes, there seems to have been a lot of water in the early history of Mars. I mean, they did a lot of other things, but from the water point of view, that was their job. And then Curiosity which went in the 2010s and teens and is still operating after 10 years. That really demonstrated that the conditions that would have allowed life seem to have existed on Mars. And so what Perseverance is supposed to do is to see if we can actually find evidence. It's a long shot, but that's what it's designed to be able to do. And in order to do that, you have to choose a landing site which is at least capable of producing, of preserving ancient life or remnants of ancient life, fossils, so to speak, if it existed. And that happens to be in the ISRU crater, which you can see here. It's very clear that at one point this looks like a riverbed, and it deposited a delta. And that delta, we know from orbital observations, primarily made of clays, carbonates, which we know, at least here on Earth, are very good materials for preserving fossils. So that's where we wanted to go. But this is a pretty rough area. There's a lot of nasty stuff around here where you don't want to land, and that meant that we needed a really precise landing ellipse, much smaller than we had ever done before. Even with Curiosity, you can see, you know, some of the earlier, Curiosity was much bigger. The early Pathfinder was a huge error ellipse. How did we manage to do that? Well, there's a new technique now which was used called terrain relative navigation. Typically, when a spacecraft was coming into Mars, you have a state vector, and then you have inertial navigation, and as it comes through the atmosphere, the inertial navigation keeps track of its position and takes you as close as possible to the desired landing spot. But inertial nav drifts over time, and so in order to get this really precise landing, what they do was, while the rover is still on the parachute, they loaded in the parachute, loaded in the rover's computer memory is a picture that had been previously taken from orbit of the terrain that it's expecting to see. It then takes its own picture of the terrain, compares it to the picture of the broader area, and that tells it exactly where it is. And so it updates its navigation state vector while it's still on the parachute. So then it drops off the parachute, and now you can get a much more precise landing. And that's exactly what we were able to accomplish. So again, I hope all of you have seen these incredible pictures that they had such good photography all the way down. They also had an audio recorder that unfortunately malfunctioned, so we didn't actually get the sounds of re-entry, but we sure got some nice pictures. This is taken from the sky crane looking down, and this is taken from the rover looking up. I want you to notice, by the way, you know, this sky crane was active, but you don't see any exhaust coming out of the rockets, and that's typical of hypergolic fuel. You see a big flash when the engines ignite, but after that, it's pretty much transparent. But when the artists do their conceptions of, and this is, you know, right after you hit the ground, you cut the cable and the sky crane flies away, but the artists have to draw those, you know, the flames coming out of the rockets, otherwise it just doesn't look right. But remember, most often when you have the small thrusters firing in space, you don't see anything. Anyway, off goes the sky crane. We thought never to be seen again, but it turns out that it actually crashed right over a nearby hill, and one of the cameras happened to snap a picture. You can see the dust and stuff being split up, and actually the rover recently drove by and actually took some pictures of the bits and pieces of the parachute and some of the other stuff. But anyway, we nailed it. That was a very, very exciting day. You know, where are we going to make the landing? I was on a Zoom conversation with lots and lots of colleagues who had been working on this project for years. And so one of the people, we were sharing images, and so one of the people took a picture of our image, that's my wife and me, celebrating with champagne. By the way, I had a bottle of whiskey in the closet just in case we didn't have a successful landing. It's still there. So anyway, so here we are on the surface of Mars. All right, here's the front of the delta, and up there you can see the outer edges of the crater. And this is Perseverance. So just a brief introduction. Lots of geological-oriented instruments. It has a robotic arm. They have Sherlock, which is an ultraviolet camera that can study the chemical composition. They added a visible camera to that, and what are you going to call something that goes together with Sherlock? Well, obviously it was called Watson. And then we have Pixel, which is an X-ray spectrometer, so that you can actually put it close up to the surface and get from the X-ray emission, nuclear X-rays, you can see the atomic composition. Other things, mass cam for taking panoramic photos, a super cam, which actually it can do many things, but among which it can actually shoot a laser at rock and vaporize the rock and then take spectra of the actual emission from the vaporized gas. That's emission spectra, by the way, just referring back to this morning's talk. A lot of these experiments are basically improved versions of the same type of experiments that were on Curiosity, but we have a few totally new things. We have the RIMFAX, which is basically a ground-penetrating radar, so that as the rover moves along, you can look at the underground strata that you're going over, and that's very important for the geologists. Also, if by any chance there happens to be some water or ice under the water, RIMFAX will be able to see it. So far we haven't, and then we have META, which is an atmospheric experiment, and of course MOXIE, which you can't see here because MOXIE is inside the rover. Almost all of it is inside the rover, but I'll show you more about that later. So META has been studying the atmosphere ever since we've been there. They get these nice pictures of dust devils. Almost every day we get a dust devil or two. And, here we are on Mars with lots of nice things to look at. The geologists would love to have gone up to that hill, but of course there are a whole bunch of engineers who are called the RPs, or the rover people, who basically just decide, is this a safe place for the rover to drive or not? You look at that and you say, yeah, sorry guys, we're not going there. But we've gone to a lot of interesting places. Of course, the scientists love to personify some of the things they see, and you look at these little rock formations, and, well, you can see as well. I mean, who would have thought you had penguins and beavers and guinea pigs and all those neat things on the surface of Mars? My wife happens to be English and has a thing about hedgehogs, so I was delighted one day to be able to bring her home this picture of the hedgehog on Mars. The scientists, the geologists, spent about 3 hours debating on what made the holes in that rock. Was it wind erosion? Was it water erosion? Was it gas that evolved when the rock was cooling? And so on and so forth. And the hard part, and this is something you have to understand about doing geology on Mars, you can't just go up and pick up a rock and look at it. Honestly, it took them almost 6 months to decide whether or not the crater floor in ISRU was sedimentary or igneous. It's igneous, by the way. But, that's something that a geologist would know, in a couple of minutes just by looking at a rock with a magnifying glass. But it's hard, and, you try to figure out the history of a rock that's been sitting on Mars. What kind of analogs do we have here on Earth that allow you to draw any sorts of conclusions? Well, most of the geologists have spent time in the dry valleys of Antarctica, which is about as close to the Mars environment as you can get. But you know, this environment has existed maybe for a few tens of millions of years. I mean, for most of the history of the Earth, there was no ice and snow on the North or South poles, right? And so, you know, you're looking maybe, they find analogs and they say, oh yeah, that rock on the left, that has vesicles. Maybe that's the same thing as the hedgehog. But you know, that rock maybe was lying around for 10 million years at most, who knows? That hedgehog rock, that's been sitting on the surface of Mars for maybe 3 billion years in a almost complete vacuum, bombarded by all sorts of radiation. So, you know, have a little sympathy for the geologists in trying to do geology remotely with, you know, very, very capable instruments, but nevertheless, you can't actually get your hands on anything. Of course, the other limitation that we have with the rovers is there's a lot of ground that the rover can't cover, both because it's too rocky and also things that are far away. You know, what's on the other side of those hills? And that was the reason why another absolutely unique thing was carried to Mars. And I'm sure you've all seen pictures of the Mars helicopter, the Ingenuity, which is absolutely spectacular. You know, here's the early days of it where they dropped the protective cover, and then they dropped the helicopter itself, and it was all folded up, so it had to unfold. And then we drove away and left the helicopter there. And, you know, you've hopefully seen these before, but I can't not show one of the early flights of the helicopter, because the critical thing to remember is, there it goes, up in the air. Nobody's sitting there with a joystick. This is not your typical drone, right? I mean, this is pre-programmed from the Earth and has to be able to navigate. It has to be able to find a safe landing place. They originally expected that this 5th flight was going to be the final flight, and they were just going to take off and fly out into the distance, never to be seen again. But it performed so well that they've kept going, and I think we've had, last I looked, we had 29 flights. They typically fly at noon so that you get a shadow in the ground, which helps the navigation. And this is a cool picture that the helicopter actually snapped looking back at the Perseverance rover. So like I say, it's done dozens of flights by now, and they've gotten more and more complex. They've now flown away from the rover. They've flown over ground that the rover can't get to. It's turned into a real scouting asset for the whole mission, which of course is what you'd like to do, and NASA is now working on more complex versions of helicopters that actually may be able to pick up things, and I'll talk about that a little later. But I want to go back to that really magical day, the 19th of April, when, you know, helicopters doing all sorts of things now, but that was the very first flight, and nobody knew if it was going to work. And, you know, they didn't fly for hundreds of meters or anything. All they did was they started on the ground, they took off 5 meters, hovered for a little bit, turned back and forth, and landed. But that made history. It was like the Wright brothers. This is the first controlled, powered flight of an aerodynamic vehicle on the surface of another planet. So that was history. And the very next day, we made history because that was the first day that we produced oxygen on Mars. Now, I wish that oxygen were as photogenic as a helicopter, but oxygen is just a transparent gas. So all I can, you know, I'll be able to show you, you know, the plot of making oxygen, but I do want to explain how we did make oxygen. So, I mean, how does MOXIE actually work? So, first thing you have to do is pull in the atmosphere from Mars, and we know that Mars has a lot of dust in its atmosphere, so we have a HEPA filter That's the only part of MOXIE which is outside the rover. A HEPA filter so that the dust doesn't get through. And the way we pull it in is we use a scroll pump. That's two of those little spirals, and one of them goes around inside the other and takes a chunk of gas, compresses it, and spits it out the other side, where it then goes into the electrolysis unit. You're all familiar with electrolysis. I'm sure back in high school chemistry, everybody electrolyzes water, right? You hook up the electrodes, you hook it to a battery, and oxygen comes out one side and hydrogen comes out the other side. It turns out you can electrolyze carbon dioxide. It's a lot more difficult. You have to heat it up to about 800 Celsius. You have to run it over a special catalytic bed in the cathode with a special nickel and some other rare earth elements. And this is basically the way MOXIE works. So you get a carbon dioxide molecules coming in, heated up to 800 degrees, exposed to the catalyst. They actually dissociate into carbon monoxide, CO, and oxygen. Now the oxygen picks up some electrons, and there's a special electrolyte, this yttrium stabilized zirconium, which has a crystalline structure which only permits oxygen atoms to go through. It doesn't let electrons by themselves go through, only negatively charged oxygen ions. So they are pulled through by the electric field, and they come out on the anode where they give up their electrons, and you end up with oxygen. So this is one layer of the whole system. The actual MOXIE experiment, here the top layer is split up so you can still see the cathode and the anode, but there's actually 10 of those layers, and we basically flow Mars atmosphere in over the cathodes, and there's little nubbins which kind of distribute it so that it's evenly distributed over the entire surface, and then it goes through and we pull out oxygen. We'd like to make as much oxygen as we possibly can, but you have to be careful, because if you make too much oxygen, not only are you going to strip one of the oxygen atoms and end up with carbon monoxide, you can end up stripping that second oxygen atom and end up with pure carbon, and this is what happens to the electrical plates. You can see there the little nubbin pattern which diffuses the gas as it flows over. On the left you have a good set. On the right, that's what happens when you start depositing carbon. So we have to operate extremely carefully and produce as much as we can, but not too much. And as I said, this is the best I can do as far as, something that's photogenic. But it was sure exciting when we turned it on for the first time, and sure enough, we could measure that there was current flowing. And the only way that the current can flow is with those negative oxygen ions, and so we knew that we were producing oxygen. For every amp of current you get, you produce about 3 grams per hour of oxygen. So, and that's how we control it. What in the world is this? Oh, okay. Made oxygen, right. So actually we just made oxygen 2 more times this year. So we've run it 10 times, and we're getting ready to run it again, I hope, in another couple of weeks, because the Mars atmosphere goes through cycles of density. And of course, the denser the Mars atmosphere is, the more carbon dioxide we can pull in and the more oxygen we can safely make. The reason that the density of the Mars atmosphere can vary by almost a factor of 2 over the course of a Mars year, far more variable than here on Earth. And the reason is because of the seasons on Mars. When it gets really cold, either in the northern or southern hemisphere winter, a lot of the carbon dioxide basically freezes out as dry ice. And so the atmosphere becomes thinner, and the dry ice is on the poles. And then when springtime comes along, the dry ice sublimates and the atmosphere gets thicker, and we're now coming up in another couple of weeks on the maximum density period of the whole Martian year, and we're hoping to make we're going to actually push MOXIE to its limits and see how much oxygen we can really make without creating, I hope, carbon. But typically, we're making about 6 grams an hour, which is roughly about what you get out of a small tree. And in case you're wondering, it's enough maybe to keep a small dog alive. Not that we have small dogs on Mars, but if we did, we could keep them alive with MOXIE, okay? And there's the MOXIE, which the dog is very happy. Okay, we just have to hook him up to his MOXIE and he's good to go. Well, what he's going to eat, I'm not really sure, but in any case. So that gets us back to how do we get Mark Watney? I keep coming back on this because I love the movie, but the point is 6 grams an hour is not going to fill up 30 tons of a Mars ascent vehicle in any reasonable amount of time. You really have to scale this up by literally over 2 orders of magnitude. We produce on the average about 6 grams an hour. The idea is what you'd really like to do is on one of those 26-month Mars cycles, send your ascent vehicle to Mars, get it on the surface with an empty oxygen tank, and then start producing the oxygen and fill it up in time for the crew that comes in 26 months so that they'll have a fully fueled vehicle ready to go. And to do that, you're going to have to produce several kilograms per hour rather than just 6 grams an hour. So that's where we get this 2 orders of magnitude. But the company that built MOXIE, the actual electrolysis unit, Oxyon in Salt Lake City, is already working on this on a NASA contract, and you can see they've got a huge stack up there, and we figure about 3 or 4 of those stacks will produce 2 to 3 kilograms an hour of oxygen, which is really what we would need to do all of this. So I'm going to leave MOXIE just for a little while, because there's one other aspect of the Perseverance mission which is absolutely unique and potentially historic, and that is for the first time we are getting ready to bring samples back from Mars. You know, we've done it from the moon, but it's never been done from Mars. So there's a very, very complex system of drills and other handling apparatus, which I can't go into great detail, but you know, basically you have these little drill bits and you drill a hole, you pull up the sample, you put it in a glass container, and then you store it where ultimately, and I'll talk a little bit about that later, ultimately they're going to be hopefully picked up and brought home. Here's an animation which will give you some idea of the complexity of what they're actually doing. So we're zooming in here on the rover. Okay, and there you see pointing at us now is the drill end on the, you know, they have some scientific instruments on the end of the arm, but if you turn it around, you have all the drilling and coring apparatus. So you go down, you pick a place that you've studied, you've done an abrasion, you've done the chemical analysis, you decide that yes, it's worth sampling and drilling, so that's a view drilling down into the rock. The sample is contained inside that drill bit, so that you then take it back, and now it's got to be thoroughly photographed, curated, stored. Again, all of this done completely robotically. That's the actual sample that you see, that little white thing there. You're going to weigh it, take pictures of it, and then eventually put it into storage, where eventually it's going to be dropped on the surface to be picked up and brought it back home. And these are some of the things that they have to do. The very first time that they took a sample, it turns out that the surface regolith of Mars has a lot of surprises. and they actually picked up a sample, and the sample just dropped right out. Luckily, and everybody was concerned because they have a limited number of sample tubes, but one of the things they're supposed to bring back is a sample of the Mars atmosphere. And since they lost all of the regolith, they now had an empty tube, so they put a cap on it and they decided, all right, this is our atmospheric sample, so we didn't lose anything. Anyway, there goes the rover on into the distance. And sometime hopefully near the end of this decade, a combination of NASA and the European Space Agency is going to launch a Mars sample return mission, which will be, if you think these rovers are complicated, just wait. So this is going to land. Now, this was the original concept of what was going to be done. The European Space Agency was going to supply what they call a sample collection rover, which was going to go around, pick up the rovers, deposit them in that ascent vehicle. Unfortunately, because of the whole problems with ExoMars, which I talked about earlier, that's taking a lot of financial resources from ESA to recover, and they don't have the resources to provide the fetch rover. So I don't have another artist conception of what they're going to do because they haven't quite figured it out yet. The current thinking, and this is continually changing, the current thinking is they're actually going to they're going to send 4 helicopters to Mars, and the helicopters are going to pick up the samples and put them in the Mars return vehicle. Whether or not that's going to be the way we finally do it, and it also means that Perseverance now becomes prime, because Perseverance is going to have to carry those samples all the way until the Mars sample return mission gets there. It's actually going to leave an initial cache. Right now, every sample we take 2 versions of that same sample, because the first 9 or 10 samples, they're going to drop one of those samples off on the delta somewhere. I'll show you a picture of that in a moment. And then the mission will hopefully continue for many years. Curiosity's been going for 10 years, and they'll continue to collect other samples, which hopefully will be picked up. But just in case the Perseverance rover should die within another year or so, we want to at least drop one bunch of samples so that there's something for a Mars return mission, sample return mission, just in case we have problems with the rover. But anyway, the idea is you're going to put the samples in the Mars ascent vehicle, take off from Mars, and we are still working with ESA on this mechanism for, you can see here, they shoot out the little little mini spacecraft with the samples in it. We've got a real concern with planetary protection. Nothing that has been exposed to the surface of Mars is allowed to be exposed to the Earth's environment except when you open it up in a special high containment laboratory like they did with the lunar samples. So it's a very complex mechanism how you go through all these stages of transfer and get it back to the Earth without actually making any potential contamination. But it's then picked up by a spacecraft which will then take the sample to the Earth, release it, and it will then crash down to the Earth and come down somewhere in the desert in Utah, where it will be, and of course the part that's exposed never will have seen the surface of Mars, only the stuff that's inside it. And that will be taken to laboratories and will be studied for many, many years to come. So, just a review of what we've been doing over the course of the time on Mars. This is where we landed. This big area here is too rough for the rover to go over, although the helicopter flew right over it. But we spent the first year basically going around to the south and around the southern edge, and then we actually went up into that area to take some samples. Now we've come back, and then they spent a couple of weeks just in a race, and this was really, fast driving. At one point, they got over 200 meters in a day, which is a new speed record. But they went all around the rough region, and we're now up exploring and taking samples from the front of the delta. And eventually, the idea, as you can see, we will go up onto the delta, where we'll drop the initial collection of 9 or 10 samples so that we have something if Perseverance should die. But hopefully it won't. All the other Mars rovers have done pretty well, and Perseverance is in great condition. And then we'll basically head out and start, this is just a notional, we may not go there. The one thing that they know is that in 7 or 8 years, they're going to have to end up in a place that's suitable for a Mars sample return mission to land. And so that's, people are already thinking about that. But basically, that's looking ahead to the future. So for now, you know, the Mars, that's a selfie taken by Perseverance. A few things to say about humans and robots. I mean, I love robots for exploration because, you know, they've taken us to the surface of Mars, and we can't yet get people there. But if you think that that makes a very simple mission, this is how many people it takes to operate a rover on Mars, okay? So it is a very human-intensive mission. There is no such thing as a purely robotic mission. It's just that the humans are here on Earth and the robot is on Mars. But you know, when I look at that robot on Mars, I mean, it is such a powerful set of instrumentation, and yet we're only using it at a fraction of its capabilities. And why is that? It's because all the people are here on Earth. And if anything happens to that rover, if it gets stuck in the sand, if something breaks, we can't fix it. And if we develop new instruments that would do better than we have on there, there's no way we can change them out. We have to build a new rover and send it in another 10 years or so. So my real vision for the future of humans and robots on Mars is more like this. Now, these guys aren't on Mars, of course, but if you imagine that they're in spacesuits and that's an actual Mars rover, now think what they could do. I mean, you can be much more aggressive with what you do with your robotic resources if you have people on the spot who can dig them out of the sand if they get stuck, who can change a tire if, you know, the Curiosity wheels suffered a lot, and that has constrained them from some places where they'd like to explore because they've got to look after the health of the wheels. Perseverance wheels are tougher, but if things break, they can fix them. And, you know, anytime you can send new instruments from Earth to Mars, and they can then be installed. You don't have to wait for a whole nother new Mars mission. You can keep this up to date. That's exactly what we have done with the Hubble Space Telescope, where while we were servicing it, we could constantly not just fix things when they break, but the real value of servicing was every time we went up there, we put in new instrumentation. So when Hubble was first launched, it had 1970s instrumentation. Even if the optics had been perfect, it was limited to what it can do compared to what we can do now. The most recent Hubble mission, which was in 2009, put in a whole new set of instrumentation. Hubble is now a 21st century telescope rather than a 1970s telescope. And the same thing ultimately could be true in operations on the surface of other planets. So I don't know when that's going to happen. I don't know what kind of a vehicle we're going to finally land on Mars with, whether it's going to be a capsule or whether SpaceX is going to send their Starship. But one thing I do know is, you know, whenever those first people get to Mars, whenever that may be, the one thing that I want them to remember is, please, when you finally go to Mars, don't forget your MOXIE. And I guess we have some time for questions. I'm at your disposal. Oh, we got one of those cool catch boxes.
Yes.
Who's gonna toss it first?
We're not throwing that. Okay, let's start with Philip. We learned not to do that.
Yeah, hi, thank you so much for the lecture and the distinguished lecture. Both were quite fun. This might sound like a dumb question, but you mentioned that there's basically a reason why you land on the lowest surface of Mars. Could you explain a bit why?
Why we what?
We choose the lowest side of Mars to land.
Why we landed in Jezero crater, you mean?
Yeah.
Well, I said it's because of that delta, which is there, which is an ideal environment, at least so far as anything we know from studying similar environments on Earth, both in terms of the fact that, you know, if you just dig in any particular spot, you're only going to find what was there. But a river delta, you're taking material from a wide area and all depositing it in one place. So hopefully by sampling the delta, we're going to get, and we haven't started sampling the actual top of the delta yet, but already they've seen a lot of different types. And finally, we're in a region where we're getting some sedimentary rock in the delta. They're still trying to figure out whether there was ice there or whatever, but that delta was chosen specifically because of the possibility that it may be able to preserve fossils if fossils ever were formed on Mars, which of course we don't know, but if you don't try, you're never going to find anything.
Hi, thank you first off for this amazing lecture. I was wondering why you opted for that very specific sub-process to extract oxygen, because I'm very sure you made a trade-off analysis. There are different options.
Yeah, there are numerous chemical processes which can produce oxygen, and this is only one of them. This one happened to be ready for testing. It may not be the best one. The other thing, of course, you also want methane as a propellant, as a fuel. Now, the thing about methane, you know, oxygen we can get right out of the carbon dioxide. We have carbon and oxygen, and you just take the one oxygen atom. To get methane, you need hydrogen, and that means you're going to need some water. And we know there's ice deposits on Mars, but from what we know now, the only ice we found has been at pretty high latitudes in the northern hemisphere, and presumably similarly in the southern hemisphere, although we haven't directly explored that. Which means you got to actually go there, set up a mining operation, pull up the ice, clean it, refine it, electrolyze it, and so on. And that's a pretty complex operation. I'm sure someday that's the way we'll do it. And then with water and carbon dioxide, you can make both oxygen and methane, and you've got the full propellant system. But the nice thing about what MOXIE is doing is it doesn't matter where you go. There's atmosphere all over the place. So you can be anywhere you want, and you can produce oxygen. And so this is a particularly nice process from that point of view, because it only needs the carbon dioxide. You don't need water.
We have a question from online. Is there a reason we use rovers with wheels as opposed to a walking design or hexapod-like design?
Yeah, the wheels are the simplest type of. I don't want to make the claim that these rovers are simple, but a wheeled vehicle is mechanically much simpler than a walking vehicle. And there's no question that someday we're going to have robotic, you know, animals walking along Mars, because they can go places where rovers cannot go. Or we'll send helicopters, which can, you know, go to places. And if we have more powerful helicopters, we can presumably, pick up samples and do the sorts of things which right now we can only do with the rovers. But wheeled vehicles are certainly the easiest way to start because, well, they have wheels, and wheels go round and round, and they're pretty easy to do. complicated suspension systems and all of that, but for now it's wheeled vehicles. But for sure, there will be other robotic assets on Mars someday.
Hi, I'm Danish from Japan, and I have one question. I have read a paper saying that they discovered some lava tubes on Mars and could be some ice inside. They have a lot of area, like spaces under the lava tubes.
Mm-hmm.
Can you give me any future exploration idea or any viewpoints?
Like I say, I mean, there have been pictures of these holes on the moon as well, but as far as Mars goes, from everything we know now, the water and the ice deposits, including those pictures of holes that you see that lead to lava tubes, are at the more northerly latitudes. Right now, because of thermal considerations, we tend to land and probably will put humans relatively near the equator. That's why the whole problem with, if you really have to go up to northward of 40, 45 degrees north latitude to find your water, that's a big deal. You've got to travel up there, you've got to set up a mining operation. The thermal environment, particularly in the winter, is going to be a lot tougher. But maybe those lava tubes not only are useful for finding water, but also as a place to stay away from radiation. So there's been a lot of work done on what you could do with lava tubes, also on the moon.
My question is a little bit related to two things you have already said, and is where are there planned any future missions to try to create methane on Mars, or maybe try to germinate some kind of grain and landing in the poles where there is water, trying to do these kinds of operations? Anything planned?
Well, people have certainly talked about growing things on Mars. There have been experiments up on Devon Island, for instance, with a Mars greenhouse. And I mean, there's no question you could do it. You got carbon dioxide. We have water, although, as I say, water is in short supply down near the equator. You got to go and get the water. But yeah, I mean, people are certainly thinking about that when we finally do send people to Mars and we get to the point of having a permanent scientific base. I'm sure they'll set up a greenhouse and try to grow things. Whether we'll get local water from Mars or whether we'll bring water from the Earth initially and recycle it over and over again, that remains to be seen.
Hello, sir. This is Sangeeta from India. You were mentioning about 800 degrees centigrade inside the MOXIE setup. So could you say something about thermal management done, because that setup seemed to be very small?
I'm not quite sure what you're asking here.
The thermal management for that 800 degrees centigrade?
The thermal management?
Yes.
Yeah, well, MOXIE has to operate under tremendous constraints because we're inside the orbiter. We're inside the rover. The advantage actually is that inside the rover, pretty much near room temperature, so we don't worry about MOXIE getting too cold. On the other hand, we produce a lot of heat, and if we are operating in the middle of the summer on a hot summer day near noontime, we actually are constrained from operating. The biggest constraint, though, is electrical power, electrical energy, I should say, because, like I said, you put 1 amp through the system and you get, you have a certain number of electrons, and it takes electrons to work the process. You get 3 grams per hour of oxygen for every amp that you're using. The rover has limited energy capacity. The energy on the rover is ultimately generated by a radioactive thermoelectric generator with, decaying plutonium, which is pretty typical. It only puts out on the order of 200 or so watts. And MOXIE uses about over 300 watts when we run, so we run off the batteries. And that basically limits how long we can run, because first of all, it takes us about 2 hours to heat up to 800 degrees Celsius, and the amount of energy we can then only run for, the most we've ever run is about an hour and a half of actually producing oxygen. That's the most severe limit, more so than the thermal constraints. If you had a permanent MOXIE set up on Mars, it would actually, you'd heat it up once and you'd keep it hot, so you wouldn't waste all that electrical energy just heating it up, and then after we run, it cools down, and we got to heat it up the next time, and so we use up a lot of energy. And that's why we can only run fairly infrequently, because when we run, we use so much energy that the other experiments have to shut down, and of course, you know, they want to do their geology and all that other stuff, and so we are severely limited. Also, the design of MOXIE was limited because we're inside the rover, so we have a limited amount of power and a limited volume, a limited mass. So it's a test. Ultimately, actually, one of a student of mine who just got his doctorate, he wrote his doctorate on looking at a scaled up human scale version of MOXIE and did an optimization to show, you know, what kind of a compressor should you use, what kind of electrolysis should you, and so on and so forth. And for sure, it's going to be possible to do that, to scale it up. And when you do that, it will be much more efficient, because at that point, most of the electrical energy that you use will go directly into making oxygen rather than just heating up the system, which is what we use most of the electrical energy for nowadays with MOXIE.
Rogier Berlijn from the Netherlands, nice to meet you. First of all, thank you for, I think, the most adorable lecture slide of the last 3 weeks. My question actually pertains to the scalability of the technology, in the sense that I was wondering, is there any limitation to potentially scaling this up to planetary scale, so you could start
If you're talking about terraforming Mars, you know, people often ask me about that, and here's my answer. If you give me an infinite amount of energy, I'll terraform anything. But, you know, to make, you know, what are you going to do? Suppose you could make an atmosphere of Mars, the solar wind is going to sweep it right back away. So how much energy would it take to recreate a magnetic field around Mars to protect Mars the way our magnetic field protects us here on Earth? I don't know, but it's way beyond anything that our civilization is capable of today. I don't want to make any predictions for what human beings will be able to do 1,000 years from now, because, you know, if you look at what our technology was 1,000 years ago, people never could have imagined what we're doing today. But with any technology which we can currently imagine, forget about terraforming Mars. It's not going to happen. What we will try to do is to produce Earth-like environments in closed regions, you know, underneath a dome or inside a habitat, something like that. But that's about all we can really imagine doing with any technology that's available to us today.
Sorry. So, just a quick question. Of course, chemically is the right way of doing oxygen on Mars, but have you ever considered using cyanobacteria or other methanogens?
Oh, absolutely, absolutely. And there's no question, like I said, if we have a settlement on Mars with a scientific base, we'll almost certainly have a greenhouse to grow food, green plants. We'll produce, it's easy to produce enough oxygen to breathe. Like I say, you only need 800-900 grams a day to breathe. But to produce 30 tons of oxygen in a greenhouse, no, that's not going to happen.
No, I was thinking...
And even with any biological processes which we can currently imagine, you're just not going to get there in any reasonable amount of time.
I was thinking more on terms of mass producing, as we know it's possible, using the fermenters, or something like that, that are storable microbacteria we know that could suffer.
If you can figure out how to genetically engineer, you know, bacteria to produce you know how big a bacteria farm you would need to produce your 3 to 4 kilograms an hour of oxygen, go for it. You know, more power to you. Right now, we don't know how to do that.
Evening, such a wonderful and insightful presentation. Thank you for sharing. My question was around the handoff or the trade-off between robotics-led exploration and human-led exploration. You mentioned some of the things that might be possible when you have robots and humans working together. But in terms of the spectrum, if it's relatively simple exploration and experiments, it's a lot energy and financial-wise cheaper and easier to send robots. But as you get more complex, the amount of AI and automation you need, the cost, and the effort for that might be much more than the same effort for the life sciences for humans.
Look, I mean, I love robots, and there's always going to be places where humans can't go, where we're going to send our robots, and we're going to use as much artificial intelligence and smarts that we can put into robots as we possibly can. The problem that I have when people are, tell me, oh, look what robots can do, why don't we need people? I think most people have the concept that our current level of robotic technology is like, R3CPO and R2D2 in Star Wars, that, they can act and think almost like human beings. Even our best artificial intelligence, it's very good at playing chess and it does incredible things. And the more intelligent our rovers are and the other robotic assets, the better it will be. If we ever get to the point where we have a robot that really can think and act like a human, we're living in a very different society than anything we can imagine today. Whether or not I look forward to that, I don't know, but that would certainly, if you had a robot that could do everything that an astronaut could do, great. Send them not just to Mars, but send them to a lot more difficult places like the surface of Titan and the icy moons of Jupiter, where we're never going to be able to send humans because of the radiation levels and so on. So, yeah, I mean, the better the robots are, the more exploration. I don't have any problem with that. But right now, there are just things that rovers and robots can't do. And that's just the way it is. But if you can make better robots, please go for it. We'll use them.
Is this working? Oh. Hello, hi. Oh, God, that is loud. Hi, I'm Tom. I'm from London. Thanks again, like everyone else said, for a great lecture. That point on popping champagne or whiskey was particularly relatable. I was in Edinburgh watching it on TV, so, My question is about the planetary protection point. Is that a settled issue, and what kind of consultations were there?
Your point was about what?
Sorry, the planetary protection element of the Mars sample and return. Is that a settled question, and what kind of international consultation did that involve?
Well, you asked, is that a settled question? I certainly would not say yes, because we really don't know what exists on the surface of Mars. We'll have a much better idea when we bring back the first samples and see if there are any microorganisms in it which might contaminate the Earth. Right now, we're much more concerned, as far as planetary protection, with protecting Mars against Earth organisms, because the last thing you want to do is to contaminate the regolith of Mars with an Earth organism, and then you dig up a sample and you bring it back to the Earth and you analyze it and you say, oh my God, there is life on Mars, and it looks a lot like life on Earth. And I mean, if that were true, that would be an incredible scientific discovery. But how do you know that it's not brought from Earth? And actually, they've done very precise isotopic analysis of various materials that are going to Mars, with the hope that if we ever do find something, we would be able to demonstrate that no, it did not come from the Earth and that it really did come from Mars. But that's a very serious consideration. We don't want to contaminate Mars with Earth organisms and then be looking for life on Mars. Oh yeah, Well, there's, you know, as in, you'll hear a lot about international law in some of your lectures, and there's nobody who can enforce international laws. COSPAR, the Committee on Scientific Research in Space, has guidelines which have been agreed to by spacefaring countries. But can we verify, for instance, that when the Russians or the Chinese send a rover to Mars, that they have done the same sort of decontamination procedures that we do at NASA? I hope they do, but there's no law. I mean, there's no way that you can enforce that. There are international agreements where people say, yeah, this is what we should do. You know, it's the same problem you have with a lot of things in space. You'll hear a lot about space debris. You know, there's no international law which prevents people from causing more orbital debris. But hopefully, you know, people abide by rules of conduct, and it doesn't always happen, but we try to limit that. And that's about all we have now in terms of international. There's no real regulatory body which can say, yes, you can do that. We have internal regulatory bodies at NASA, the Planetary Protection Office, which sets the standards for, you know, how many spores per square centimeter you can still allow to be on the outside of the rover when you're going to launch it to Mars. So you know, this is done internally at NASA, but there's no international regulatory agency that comes and checks that NASA has done it, or that could introduce any sort of a penalty if we don't do it right.
Andre Colin from Israel. Thank you very much for the fantastic lecture. My question is, you mentioned many times the Mars Return Sample mission, and one of the main part of it is a Mars Ascent vehicle, small rocket that is going to go from Mars for the first time in history. And as far as I know, it's currently planned to be a solid fuel rocket.
That's correct.
So instead, the natural question is, why not use a bigger MOXIE version that you referenced to produce fuel up there, and that could be a prototype for the future human mission?
I would separate the two. Solid rockets are simple, they're reliable. It's a demonstrated technology. Bringing that those samples are so valuable. We want to bring them back using the most reliable technology we have. But yes, the next thing we need after MOXIE is a larger scale demonstration, and at the moment nobody's planning to do anything, but the obvious next step would be to demonstrate the real production where you could ideally fuel up a rocket and launch it, but we haven't done that. But for the sample return, no. I want to do that the simplest, safest, most reliable method as possible. And you don't need a very big rocket, because you know, you're only talking about a few grams of material that are coming back. So you know, you're not launching Mark Watney off the surface of Mars with a 50-ton rocket. So you know, there you don't want to use solid fuel because it's not as efficient as liquid propellant. But just to get the samples off Mars, we'll go with the solid.
Yeah, so another reason why we use the solid is because we're not quite sure how long it will have to sit on the surface before all the samples show up. So it will have to withstand perhaps a long time period of various temperature up and downs. And the solids
Another
do the
good
best.
point.
Yeah,
And Jim, of course, as the Mars guy, knows all this stuff cold. So once I leave ISU, if you get any more questions you want to know about Mars, you go and ask Jim.
So we'll also,
he knows a lot more than I do.
Yeah, I'll also say that the chief scientist of NASA is the representative on the Planetary Protection Panel for COSPAR. So be happy to talk to you about any issues of planetary protection. NASA spent about $25 million to do a cleaning of Perseverance, so that anything it touches, you know, the sleeves, the drills, all the wheels, anything that touches the surface of Mars has been cleaned. So it's about $25 million. We report back to that panel what we did. We have Chinese representatives, Russian representatives, they're all there, and we expect them to report out every time on their missions for planetary protection. And
I don't know can you comment on practices in Russia and China to the extent that we know about them?
Yeah, they report out what they do and how they do that, and indeed they can demonstrate that they have met the planetary protection guidelines for where they've gone.
Yeah,
So-
which is
so-
what I've
so-
always
so far-
thought, but I didn't have the direct knowledge that
Right,
Jim does,
yeah.
so that's good to hear it from Jim.
Can I just add one thing? You heard in one of my lectures that the way international law is getting applied in space is most frequently through national legislation and national implementation through regulations. You've just heard an example. NASA's regulations are part of the U.S. regulatory environment. And what we're hearing just from Jim is that the Russian and Chinese are enforcing these COSPAR regulations that were adopted by resolution in the General Assembly, just as Jeff says, not enforceable in a court, but they're getting implemented through national regulation because they made good sense and they were achieved by consensus. So, you know, all this stuff's starting to come together. You might think we planned this.
Yeah, because you know, if you mess up Mars, we've messed it up for all humanity for the rest of history. So we better be careful.
Hi, maybe last question. Idan from Israel. Thank you very much, first of all. Maybe another question about robotics. In the mission of searching for life on Mars, maybe those bacteria in hidden caves and so, any thoughts about swarm as the progress with all the drones and helicopters, instead of making one big expensive rover which can not to be working, send like an army of wanderer, swarm of helicopter and so?
Well, I know that NASA has started talking, and Jim, you may want to add after. I'll just introduce it, and then Jim is much closer to this. But there are plans for much more capable helicopters. I talked about possibly using helicopters for the sample retrieval. Again, they're still working on those plans. I don't know how they're actually going to do it, but there's no question that helicopters, now that it's been demonstrated that you can successfully fly a helicopter on Mars, we're not going to stop. We're going to, just like with rovers, I mean, you look at what Perseverance can do compared to the Sojourner rover back in 1997, 25 years ago. And, you know, I'm sure that the next generation of helicopters is going to be as much advanced over Ingenuity as the Spirit and Opportunity rovers were compared to the Sojourner. But Jim, do you have any additions to that?
I don't have the mic, but I'll just say right now...
I think a mic is coming.
Yeah, Jenny, or Ingenuity, is 4 pounds. We now believe we can make something about 10 times bigger, 40 pounds. So that means we now have much more capable a set of instruments we can fly. And so I would expect, and in fact I know, a number of organizations are developing proposals that NASA will be considering for much larger helicopters that would indeed have the ability to do a variety of different things, from mowing the yard, going back and forth, looking for, you know, patches of methane that are being emitted through the surface, to flying into a skylight, which we call a collapsed lava tube, and then taking temperature and pressure measurements, because we believe in these lava tubes, they may have a constant temperature through day and night, which would be also a major advantage for humans to be able to live in there. And then, of course, look for signs of astrobiology, looking for signs of life in those. So a lot of things. Yeah. I'd be happy to tell.
And of course, the helicopters can go to lots of places that you'll never get to with a rover. I mean, imagine being able to fly down into Valles Marineris, where there's a much higher atmospheric density, temperatures are very different. Who knows what we'll find down there, but there's no way we're going to get there with rovers. But a helicopter, I mean, it's really exciting what we should be able to do with this. So stand by. What you've seen here is only a prelude. And every time we go to Mars, we do something bigger and better, and let's hope we can continue to do it. So with that, I think probably a good time to end for the night. This has been a busy day. This is my third lecture of the day. I'm not going to be giving that many lectures on the next few days, but I certainly will try to be here. So then I certainly enjoy sitting down at meals with as many of you as I can possibly meet and talk with. And so please don't be shy to come up and ask questions and things. That's why I'm here, because I love to talk with all of you.
Well, Jeff, I think this is the first time actually you have given this lecture at ISU, as far as I'm aware. Such an incredible one with that. Thank you very much once again for joining.
All right.
All right, thank you very much, everyone. So everyone watching us online, of course, this is not the end. This is just the beginning of our distinguished lecture series. And tomorrow, indeed, we have a very, very special event. So 11 Portuguese time or 12 p.m. Central European time, ISU will be delivering for the first time in ISU's history a lecture in metaverse. So we will be here in this auditorium, on this stage, and some of our participants will be actually experiencing it with VR goggles, and this event will be webcasted as well live. So if you're interested to have a lecture by Tora Rutley tomorrow, please tune in exactly at the same channel tomorrow at 12 p.m. Central European time. Until then, stay safe, stay with space. Take care.